All right, everybody. Today we're going to be talking about models and parameters. So that's lecture 5, and the lecture date is September 14th. So first thing, let's do a brief recap from 220 and 291. You've seen regression in these classes, but let's look at regression in a slightly different way. Y equals f of x plus epsilon. This is this general modeling problem. Or I should say the general modeling framework. So 1, we have a y outcome variable of interest. Outcome variable that we want to explain. Two, we have x, and that little arrow on top is vector. A vector, x1 through xp of predictor slash explanatory variables. So an example could be y equals life expectancy, and x could be a whole host of variables that you think explain who lives longer than others. 3, f is a function that makes explicit the relationship between y and x. Last but not least, we have 4, epsilon, and that is some notion of error. Now, you've seen this in your regression class often as residuals. All right. Now, this is all very general and abstract, so let's bring it back to something you've seen before with an example. Example, simple linear regression. All right, in this case, the y equals f of x plus epsilon. There's only one x, okay? But it is y equals, and I'm going to change color pens for this, beta naught or beta 0 plus beta 1 times x plus epsilon. Now, I know this is nothing new to you folks, and you might be like, oh man, why are we covering this? But the key thing to remember is that what these are called parameters. They are the numerical values that you need to complete this functional form f. Whoops. We call such values parameters, and in fact, beta naught is the intercept parameter, and beta 1 is the slope parameter. Again, the key word I want you to remember here is parameter. All right, so the idea is given data, all right, which are n pairs of observations, y and x, you want to estimate these parameter values such that y hat equals beta naught hat plus beta 1 hat times x. Sometimes this is b0 plus b1 times x. This is what you're doing in a regression. So for example, and again, I know you all already know how to do this, but let's say you have a numerical value x, and you have x equals 0, and you have y. Well, given a series of points, you want to find the slope parameter and intercept parameter of that red line. You want to find slope parameter and intercept parameter of red line. Okay, that example is simple enough, and you've seen that in 220. And in 291, you've seen situations where you had more than one x variable. And that's what we call multiple regression. But now, let's go over to another example. Let's go back to our dendrobands data. Dendrobands data. Say you collect n pairs of data, not y and x, but rather dbh, comma, doy, where doy is day of year. January 1st equals 1, and in a non-leap year, December 31st equals 365. So you're going to collect for the same tree n pairs of data, dbh, doy. The goal is the following. You want you want to create a model dbh as a function of day of year plus some error. This is our new y equals f of x plus epsilon. This is the idea of modeling. Now, what this kind of data typically looks like is that it typically looks something like this, all right? It often, I'm a little bit jumpy over here. You often have, this is, I should label my axes, all right? This is day of year. You have dbh, all right? And let's say this is 1, and this is 365, all right? You often have behavior that looks something like this, meaning it looks a little flat with a little bit of error in the beginning. The growth increases, but then flattens out like that. So over here, a straight line is clearly not going to model this relationship very well. Rather, we're going to use an S-curve. So folks, forget about straight lines. We're using S-curves. So now the functional form f we'll use is not a line, rather the generalized logistic curve. The generalized logistic curve, which has not two parameters, not slope and intercept, but rather with 5 parameters. Okay, let's write out what this functional form is. So we saw earlier the functional form for a regression line is very simple. What is it? It's just intercept. Whoops, bring that back. It's just intercept plus slope. Intercept plus slope. But now, let's write it out. Now, the point of this thing to write it out is to show you how complicated it seems, but in fact, when you understand what these parameters mean, it's not actually that bad. But as an exercise, we're going to write this out. So our y is dBH is going to be equal to L plus K minus L. That's the numerator. 1 over epsilon. Okay? E to the minus R times DOY minus DOY subscript IP. All right? That's all going to be over theta. And then we're going to take this beast and raise it to theta. Oh my God, what the hell is that? But the key thing I want you to notice is the following. There are 5 parameters. And they actually have very intuitive interpretations. The first one, L equals lower asymptote. This is something you must have seen in calculus, but a lower asymptote is that value down here. This is L. That is the starting point. If we have that, we also have, K. Number 2, K equals the upper asymptote. So that defines the peak that it hits within a year. The next one, DOYIP. DOYIP is the inflection point of curve. The inflection point of a curve is, in this case, right about, let me bring that back. Right about here. DOY inflection point. It is the point at which the curvature of the S changes. So you can see here that the second derivative is positive, but here it is 0, and then it is negative, meaning, okay, these explanations are always kind of tough, but up until this point, the slope is more positive, more positive, more positive, more positive, more positive, more positive, more, and then it keeps changing. Over here, the slope stops changing in that direction, and then it starts becoming more and more towards the negative side. Whoa, I have no idea what that is. I'm going to delete that, okay? But you can think of it as the point at which the curvature of the S changes, i.e. point at which curvature of S changes. All right. Number 4, R. That is equal to the slope of curve at inflection point. So if we go back over here, whatever that slope is, okay, and I'm not doing a very good job of drawing it, but whatever that slope is, that's R. And last but not least, 5, theta. Now, theta is a top and bottom symmetry parameter. So the idea is how much is what's going on the top part of this S curve up here symmetric to what's going on to the bottom curve. we're going to leave that one aside, but it is worth pointing out that this is a symmetry parameter. Symmetry of top and bottom of curve parameter, where theta equals 1 means symmetry. Okay, we're going to study this graphically and visually on Friday. But the point is that I want you to get out of this particular lecture is the following, is we want to estimate these 5 parameters using data. We want to estimate these 5 parameters, where dBH is equal to f of DOY plus epsilon. Did I write that correct up here? Yes, up here. That's what I wrote up here. But this is what's going to make things tricky. This thing right here is the error term. The error is what's going to make this parameter estimation problem difficult. So if you go back to the graph, you can think of error as the degree to which these black points don't fit exactly on that red curve. All right? So here's our introduction to parameter estimation, but we're going to talk more about all this on Friday.